All right. Good evening, everyone. I apologize for the lateness and the delay in getting this to you. It's almost 7 o'clock Friday night. It's been a long day already, so let's see what we got here. Okay, so I've got the PowerPoint. We're going to go through these formulas, examples, and then I had a question. Someone had questions on 3 of the questions in the homework, so we'll take a look at those. So T distribution. So if we've got some random variable going along and we've got a random sample from a normal distribution, but we don't know what the mean is and we don't know what the variance is, then when we construct a random variable t such that x is the mean of the sample, subtracting the mean of the population, which again we don't know, we've got this variation, the standard deviation of the sample divided by the square root of n, that this actually has a t distribution. And it has what's called n minus 1 degrees of freedom. So n is the number in the sample, right? There's n pieces of data. If you take n minus 1, those are the ones that are free to be are free. One of them is constrained. So what does that mean? Well, we use a table, a z table. So let me show you that, and we'll look at an example. But a z table, here we go. And I've uploaded this to the resources. I sent it out as an announcement. It's in addition to our z table, which is at the sort of further down, or it's in here anyway, so it's in the same one as the z table. So the way a t value works is it's based on the sample size. So notice degrees of freedom. If I have 1 degree of freedom, that means I have 2 pieces of data. If I have 10 degrees of freedom, that means actually I have 11 pieces of data. This is always n minus 1. And what you notice is for any particular confidence interval, the more data I have, the narrower, the lower this number becomes. Okay, so this would be the 95% confidence interval that's highlighted here in red if I was doing a one-tail test, but it's 10% on 2 sides. So this one here, the t of 0.975, is what we usually use, our alpha of 5 for a 2-tail test, 2.5 on one side, 2.5 on the other. So it's what we've been using a lot, and what you see is the more data you have, the more pieces of data, the closer this number gets to what the z table would be at that same value, 1.96. So 1.962 out of 1,000. It's still a little bit bigger. So you need a lot of data if we do for the t, so z, we can start using that if all the theory says we can use the z table. So the t table, what you want to think of it, it is an adjusted z for smaller sample sizes. Okay, and it responds to the change in the sample size. So one more piece of data and you're able to get a narrower confidence interval. You're able to narrow in on that data that you're trying to estimate, such as the population mean. So let's take a look at how we apply that. So first of all, we use it just like we did a z. We're going to look the number up, and this is the same formula sort of that we've been using, except we had a z here, right? Let me we'll go back a couple slides. Right, here's the z value times, well, that's just the standard deviation, but here it is. So z, this was a value, the standard deviation divided by square root of n. So that's all it is it's the t is a different type of number that is sensitive to the size of the sample. Okay, so let's go forward and we're going to give this one a try. Okay, so it's the same formulas that we've been working with. You subtract it, you add it, and the mean is going to be somewhere in between there. The larger the data size, the smaller this t will be, which means that the interval will be smaller as well. Okay, so let's see how that works. So we're given some data here, and they're going to do most of the work for us. We don't know the mean. This is a sample. There's 22 pieces of data. And let's go here. So, and they tell us that n is equal to 22. They did the calculations. This sample has a mean of 13.71. It has a standard deviation of 3.55. Again, they would calculate those like we did last time. This should be a n minus 1. I don't know, didn't have the font or something. So we've got 21 degrees of freedom because there's 22 pieces of data. So they looked this up, and we're going to look up in the table, and we'll see we get 2.080. And so we come back to our table. So we're looking up 21 degrees of freedom. We are wanting a 95% confidence interval. We want a two-sided, right? So that's a 2.5. So what that looks like is, maybe I need to, so we're looking at the 0.025, 95%, but a two-sided, and we come down to 21 degrees of freedom. That's this one right here. What happened? Oh, I turned it off. It's this thing, right? So 2.0, that's how they got it. They used this table, looked it up. And I use this, I downloaded it from the internet. It's got a kind of how to look it up. I don't know why this is necessarily important, but it was just an example of how to look them up for a particular value. Okay, so if we had more data, notice we would have a smaller t value, we would have a smaller interval, which would mean we were more accurate. So 2.08, that's where that's coming from. That's how you would look it up. We cleared off all that stuff, that's fine. So now let's go ahead and use it. So actually I gotta go there. Oops. This is a mess. Oh, sorry. Perfectly laid plans all went awry. Okay, so I thought I had a little formula along here somewhere, but it's not showing up. So sometimes you just need to stop, right? So what we've got is we've got x bar. So we're going to, not that, well, oh, I see what happened here. We want that, let's clear that. Okay, x bar. Oh no, I don't want it there. When I go, where do I want it? Maybe I do. I can't remember where I need to put it. Anyway, we'll try this. 13.71 is our sample mean. We're going to subtract the t value, which we looked up, 2.080. We're going to multiply by standard deviation divided by the square root of n. 3.55 divided by square root of n. Well, that's 22, right? Of course. We know what n is. Square root of 22. And that's going to be less than or equal to x, which is less than or equal to 13.71 plus 2.080 times 3.55 divided by square root of 22. Okay, so we plugged that in a calculator, we get a number, and when we were done, as you probably could have already seen, they did the calculations for us, and so 13.71, you get 1.57, add 1.57. So this is our confidence interval. and the comment says that it's fairly wide. It's going from 12 to 15, so yeah, it's not really narrowing down what the mean of the population would actually be. If we want to do that, we need to get more data. We need to have a larger sample size. Okay, and we could see that on the T chart. To get this number smaller, the 2.080, we need more degrees of freedom. Okay, yeah, so that's pretty much it. Okay, thought this was supposed to, maybe I just kind of talked through this one. So next, we may have a binomial distribution, and remember that's where things are a pass or a fail, a yes or a no, a heads or a tail. So there's only two possible outcomes, and so if one is 80%, and we call that one P, the other probability is going to be 1 minus P, or simply 20%, right? So 80% chance of rain, 20% chance of not raining. So we always see this, and so in our formulas with the binomial, we see the probability of a success times the probability of failure, P times 1 minus P. So anyway, these come from the binomial distribution, the Z. If n is large, that's the caveat here, you have to have it large. What does that mean? Well, it means really big. And yeah, does that mean 30 or 40? It could work at 30 or 40, but the larger the better. And so again, this p hat is a estimate of what the probability would, what the actual proportion would be. We get that from our sample, and we're trying to get close to what is the proportion in the population, right? So this p without a hat, that's the population. Okay, and we can use this formula, and we get a confidence interval that doing the math sort of, so I'll kind of let you go through there. So since z itself, the fact that it's between two alpha values, so this is a two-tailed test, right? That's this would, and we've been using a lot, a 95% confidence interval, alpha equal to 0.05, so it's a 5% alpha, gives us a 95% confidence interval. But we could change that, we could do something else. And anyway, so the math is, well, since z is equal to this estimate, this sort of part, this part would be in that interval, so we can use that. And then what we're really trying to find out is we're trying to get a boundary on just the proportion in the population, right? So we do some algebra, multiply both sides, multiply everything by the denominator. That brings it up over here and here, so both sides of the inequality. And then you're going to bring p over, and this, so you're think of this as negative or whatever. So this is a negative, so you're subtracting it from there. This becomes, you add it. Anyway, you do some math magic, and in the end, the population is bounded by these two sides. And that gives us our 95% confidence interval. And again, what that means is 95% of our samples would return a proportion that would be in within these boundaries. So we're going to use it. And again, it's not anything too new. It's really just this proportion. Before we did this, it was the mean. This time it's the proportion of the population. What's the proportion of people in the population that have a particular genetic anomaly? May be good or may be bad, but anyway, and again, we talked in class about blood types, blood type O, what's the percent? That might be what we're looking for. So we take a lot of samples. This gives us a boundary for what we would expect in a population. The z-score, we've already been looking that up, and then this is in place of the standard deviation divided by square root of n, but you can kind of see it's kind of in there. So the sample proportion times 1 minus p, that kind of serves as the an estimate of the standard deviation. Okay. Let's go back. Okay. So, an example. So we've got a random sample, 85 automobile engines. 10 of them have surface finish that is rougher than the specification allows, so those are fails, 10 fails. Construct a 95% two-sided confidence interval for P. Okay, so first of all, what would the proportion be? Well, that's 10 divided by 85. That's 0. 10 divided by 85, 0.11776. For simplicity, we'll just round that to 12%, 0.12, 2 decimal places, round it up. So what was our formula? Well, that's why we had this. There it is, that's why I had that. Okay, so there's our formula. So we're going to take our p hat, which is 12%, minus z f over 2, and again 95%, we've been looking at, that should be 1.96, right? So we get p hat is 0.12 minus 1.96, and again that's z of 0.025, so that's a two-sided. We looked that up. We've done this before. We have 1.96. What I go with 5? 1.96. That's what we've been using, right? Let's since I did that, let me. And again, you can always fast forward through some of these videos, and you might need to with the way my brain is going right now. So that's. If we're looking, that's a 0. We want just 2.5 here, so that's going to be 0. It's going to be, we're looking for 0.975, right? 975, right there. Yeah, so 1 point, what's at the top here? 0.96. That's what we said. Okay, I just had to check. Okay, and now my stuff is gone. Okay, so let's go again. What did we have? We had 12% minus 1.96 square root 0.12, 1 minus 0.12, which is 0.88, right? 1 minus 0.12 is that. So you always get, that's what you get when you get a binomial. Over n, we had 85 as our sample size. And that's going to be one side of it. P will be here. And then again, we do it this 0.12 plus 1.96 square root 0.12, 0.88 divided by 85. Okay, and that'll give you your confidence interval. And let's go ahead and let them do the hard work here. I click, I put it in the wrong place, so but just get you set up. You see what they're doing. So then what it tells us is the population is somewhere between 5% and 22%. So that doesn't help us a lot with just 85 a sample of 85. So we need a much larger sample probably, because a larger sample would help. So sample size does not appear to be small. The value of p hat is fairly small, which leads to a large standard error for contributing to the wide. See, so it's so large, mainly because the proportion is small. So maybe if you did this on the successes, right, that would make that proportion larger. And I guess maybe if you look at this in terms of successes, it might be a smaller interval. Okay, so we just go on this, so to be able to say for a binomial population, how big should the sample be? Well, we take our z again, and if we're doing 95% two-tailed, that's a 1.96 divided by the error that we're willing to accept. We square that, and then you take your proportions, multiply them together, the p, 1 minus p, so this is all probability of a success times the probability of a failure, and that will tell you the sample size you need. Now, what they're saying here, right below this, which was supposed to not show up quite yet, but it did, is that the largest sample size you're going to need would be if you had a proportion of 0.5, because then you get 0.5 times 0.5, which gives you 0.25. So that's actually the largest value you can get here, which gives you the largest value of n. So if you want to just say, hey, let's just, we really don't know what the proportion is, right? Because that's a population proportion. Since we really don't know, we're going to be on the most conservative side. We're going to get the biggest sample we would need, and so let's find that out. So here's this formula. Just put 0.25. That's 0.5 times 1 minus 0.5. So 0.5 times 0.5. Sorry about that. Let's go back. So this will give you the largest value of n. So as long as you have that, you're going to be safe. You could get less, and so if you know it's only 20%, maybe you want to do 20% times 80%, and then you wouldn't need as large of a sample. But this is kind of the most conservative way to do it. And so some researchers will say, hey, forget this binomial thing. Let's just use this one down here. And it says we need 300. We go get 300. Okay. So we go to this example. So we want to figure out how big of a sample do we need. So we want to be 95% confident. And again, that's what we usually want. Why not more? I don't know. Using p hat to estimate p is less than 0.05. So using p hat, which comes from a sample, maybe the last one we did, as an initial estimate of p, we find that equation 12 and the required sample size is so okay, this is one where I see what was the formula. Here's our sample size formula. We want the estimate p is less than 0.05. Okay, so what do we really need? Well, we would need an n. Again, 1.96 is our z value, z over 2. Confident that the error using p hat to estimate this is less, so we want our error to be less than 0.05. We square that, and then we multiply by 0.12 and 0.88. Okay, so 1 minus 0.12. Okay, do all the math. We'll let them do it. Let's see where to, yeah. So you can see it all coming in here. They fill it, so they did the formula. They fill it all in, and so they say we need we need 163 if this is our proportions. But again, remember, this is coming from a sample, and we just did this on the last one. The population could be 5% to 22%. And so if the population is actually, if the proportion is larger, say 22%, this won't be enough of a sample. So then they say, okay, let's be as conservative as possible. Let's use that standard equation where we're basically going to use 0.5 and 0.5. And they've already done the work for us. So the only thing that's different, you see, is that we do 0.25, which is 0.5 times 0.5. Okay, so 385. So that's a lot more though. But again, you don't want to collect 163 pieces of data and then you come up and you see that, oh, our sample is really this, proportion is really larger, and we didn't have enough. We should have got 200. Oh, okay, so what do? We throw out our study and lose our $1 million grant or something? We just go get 385. We're going to be safe. Okay, that's the way this is. Okay, so we're almost there. Just like in the other parts, we can do a one-sided confidence interval if we believe that whatever's going on, we're just looking for an upper bound or a lower bound to our proportion, and we're sure that it's not. It either just is always going to go up. It's going to be above that number or going to be below that number. So it's just the other half, right? Just one side. And notice the z it'll be a different value. So instead of using if we're using 95% confidence interval, in this case, this is just the 5% instead of the 0.25. So this is what 1.64 I think we came up with instead of 1.96. Okay. So just maybe put a note here. One side z was equal to 1.64. For two side, remember we're splitting that between the bottom and the top. That gave us a z of 1.96. Okay. So that's all this is. This will be one-sided. So that'll be 1.64. Of course, they may ask for a different confidence interval, but you'll be able to get that. Okay. Finally, this last one, there's only one question in the homework about this, but it's really nothing too new. It's just saying, again, this is a t-value, so you're using degrees of freedom, but this is to predict a future observation from a normal distribution. So we can use this. If you don't want to do the last one, I give it to you. Don't worry, it's like 30 or 31. You can skip it or you can do it. I'll let you extend. I'm not going to even talk much about this, but it's not too different. You just get this t-value from that table, s and 1 plus. So you just use the formulas, and then you're going to get your prediction, your boundary, 95, again, whatever they ask for, 95% confidence that your next value will be between these two. Again, that might be helpful if you're, I guess, that'd be helpful in the lottery, I guess. You know, you get the numbers are 95% accurate that it'll be between these values, right? So here's an example. I'll let you look over it as you like. It's in the PowerPoint's in the resources, so feel free to take a look at that. Okay, but again, I'll let it be sort of like a little extra credit. So if you need some points, go ahead and do it, and you know we'll negotiate later. Extra work is extra work. We'll get you there. Okay. You know, did this workshop on with some Kazakh scholars today. I'll show you my class. You want to see my class from Kazakhstan? That's what I was using robotics to teach them. So these were my students for a while. We had set up this, my friend from South Africa. He was what he taught. He taught computers, yeah, those things. He was, but informatics is what they called it. So he had done robotics before. So in his room, we set this up. But kind of, so many people wanted to do robotics. We had kind of had them do a test, and they had a plan through, and we said, okay, if you can do this, and we got a lot of people that carried through, and we had a nice group. And here's me a few years ago, so my hair's a little bit different color. I actually was using dye at that time too, anyway, but you don't even know that. But that was 2012. This little kid here was cool. So that's the schools would come from the districts to visit. We were kind of in the rural areas. We were at the president's school, and so we had extra stuff. And anyway, some of the local schools would come and tour us, and it was kind of fun. Yes, I taught math for like half the day, and the other half was my project. I would design robots and curriculum, and these guys back here, these were our team. They hung out there. They never wanted to go home, and I didn't have any place to go. I was just there by myself. I lived a few blocks from the school, and that's what I did for years. I'd go to school and teach, and check in with my wife from time to time. She was in Thailand. I was in Kazakhstan, and but it was a good experience. So that's what we did. Okay, I forgot I had that up. Anyway, you didn't need to see that, so we'll close it. And what you wanted to see was probably something more like this. So here's question 15. Someone had a question about this. Let's see. I think this one I can use the draw program, and it'll probably be a little bit better. So confidence interval estimate is desired for the gain in a circuit on a semiconductor. Assume that the gain is normally distributed, so that's important. Standard deviation of 20. How large must n be if the length of the 95% confidence interval is to be not greater than 40? So the length, when they say the length, what they're saying is that the confidence interval goes from here to here. It's got to be this distance has to be 40 or less. So remember, we're kind of saying, well, we've got a number in the middle, we add to it and we subtract from it. So what we're really looking for is that that the error is half of that length. Okay, so in this case, it's not greater than 40. What we want to say is that E divided by 2, well, 40 divided by 2 is that E is equal to 40 divided by 2. So we want our error to be less than 20, because you're going to add it and subtract it from there, right? So E should be 20. Sigma is 20. Z alpha over 2, since we want a 95% confidence interval, two-sided, that gives us Z as 1.96, which again you could look up again, but why? It's always going to be the same. So we get N equals 1.96 times 20, which is the standard deviation, so that's this 20, divided by 20, which is this 20, the error, half of the length, and then we square it. So actually this 20 and 20 cancel, don't have to do much. 1.96 squared, and that gives us almost 4, right? Sorry, it's almost 2. 1.96 squared is 3.84. Yeah, that's right. Close enough, and you want to round it up because that's how many n's do we need? What sample size? So that's 4. How large must n be if the length of the 99% confidence interval is not to be greater? Okay, so this time our z, since it's a two-sided, because they don't say anything, if they don't say anything, you just assume it's two-sided. So this is z, alpha is going to be actually 1, so this is 0.5. So what we need to look up for the 99%, so when z of the 99% confidence interval and alpha over 2, so that's that would be alpha of 0.005. So we're looking at 0.995. 9946 9951, 9949. I think we want to be more this way, so that's 2.58, I think. Could be 2.57, 2.58. I think we want to be more conservative, so we go a little bit higher, 2.58. So 2.58. Okay, and so that calculation comes out the same, sort of 2.58 times 20 over 20 squared. Again, the 20s cancel, so 2.58 squared is I come up with 6.65. So we better make n 7 go up. Okay, so that was number 15. But probably the question was about this when it talks about the length. When it's talked about the length of the interval, you want half of it. When it talks about the error, if it said it wants the error not to be greater than 40, then that's really talking this half, and we just go ahead and use 40 as our error. But this time, when I talk about the length of the error, or the length of the confidence interval, it's not the 40 is not the error, it's the length of the confidence interval. The error would be half of that. Does that make sense? I hope. Let's see. Let's see, they got it all here. Yeah. Let's see, what did they use? They used 2.58. Yeah, good. That's what we used. And here they got 1.96. So good. Okay. Question 20, suppose that we wanted to be 95% confident the error in estimating the mean temperature is less than 2 degrees Celsius. So this is giving us the actual error, not a confidence error. So we actually will use 2 degrees. We don't divide this in half. This is not the confidence interval is too long or something. No, the error is 2, so E is equal to 2. And they told earlier in the problem in 20 that the standard deviation is 0.5. So what do we do? 95% confidence interval is showing a two-tail, so n should be equal to 1.96, and that's our z value there. The standard deviation they gave us was 0.5. The error is going to be 2, and then we square that. So we calculate that. 1.96 times 0.5 divided by 2 is equal to that, and then we square that. I get 0.24. Yeah, because that's half of that, then you cut it in half. That's like cutting it in a fourth. They're pretty small, 0.24. Well, that means n needs to be 1. What good is data if you don't get any data? You always got to get at least one piece of data. I don't know how helpful that would be, but anyway. So that's 20. And then for this one, what is the confidence interval? So this one looks like you got to do a lot of work, but it's actually not too much work. You just need to look this number up. This is your z, and remember this is showing you it's a two-sided. So we want to look up 2.14, or do we? It's a two-sided. Let's see, what do we? Let me look it up, and then I'll decide what we're going to do. 2.14. That's our z value. 2.14. 2.14 is here, right in the middle. .14. Okay, so that's the number we've got. 0.9838. 0.9838. Now what is that? Well, again, from this table, that means 98% of the data is below here, right? How much is above? Well, we subtract it from 1. So we're going to take 1 minus 0.9838. That'll tell us how much is in this upper region. 1 minus 0.9838. That's 0.0162. And now since we're doing a two-tailed test, the idea is that that amount, this 1.62%, is on the top and the bottom. So we add that together, or multiply it by 2. Again, maybe that's cleaner. So we take that number times 2, means 0.0324. So that's the parts, so that gives us sort of this normal curve. That's how much is on these two ends together. So how much is in this middle? That's our confidence interval. Well, we subtract that from 1. Okay, so I kind of want to just do this visually so you could see what you're doing, because you do subtract from 1, you find that, you double it, and then you subtract that from 1, and you get the middle part here. So we then take 1 minus the answer, 0.0324, and we come up with that our confidence interval would be 0.9676, or if we want 96.76%. So I think when they say round to 2 decimal places, I think this is what they're looking for. They actually want the percentage. What is the confidence interval written as a percentage? Just read the instructions and you'll know what to do. Usually, if all else fails, I read the instructions. Okay, 96.76. So that's the 2 decimal places they want. It's the same thing here. We're going to look up 2.49. Down here, we're looking at 1.85. You're going to find the percentage, right, from each of these, the percent in the middle. You're going to subtract it from 1. Wait a minute. So, yeah, these are both. This is two-sided. This is two-sided. So yeah, you're going to subtract it from 1. You're going to get that number. You're going to multiply it by 2 because they're two-sided tests. And then you're going to subtract that from 1, and that will give you your percentage for those. Okay, so 2.49. Again, you just come over here. 2.4. There's 9. Is 9 all the way to the, 2.49 would be all the way to the end. So 2.49 is going to be 9936. And again, 0.9936. You're going to subtract that from 1, and you'll get a really small number. Mine goes into scientific notation, but what you get is 64, right? So you get 0.0064. Again, you multiply that by 2, and that gets you 0.0128. Subtract 1 from that, or 1, subtract that from 1, or do it the other way around. You get a negative, but then you know it's not negative. So it's 0.9872, and again, round it to 2 decimal places, but they want it as a percentage, 98.72%. I'll just do it this way, and we'll just forget about this stuff, 98.72%. Okay, same thing here, just look up the 1.85 in the table. And so it's kind of working backwards to see what your confidence interval is based on the value of z that gets used. Kind of funky confidence intervals, but you know, it works. Alright, so those were the questions I had. This is the video I'm making. I'm going to send this off, and we can see where we're at on Wednesday. Thank you all so much. Have a great weekend. Stay safe and be well. We'll be in touch. Bye-bye.